Hello and welcome to Golden Droplets episode number 24. My name is Ricardo Valls. I'm the founder and principal of vallsgeoconsultant, and today we are going to be studying SURFER from Golden Software. It's one of the best software I know for representing your results. So we will be studying variograms and different tricks that I use when working with SURFER. So let's go ahead. SURFER.
Welcome to Golden Software's introductory video for SURFER. SURFER is a powerful gridding, contouring, and 3D surface mapping software package. In this video, I will provide a brief introduction to SURFER and show how easy it is to create a basic contour map. The main features of SURFER include interpolating XYZ data with one of 13 different interpolation methods, customizing gridding parameters by limiting the search results, adding a fault or break line, filtering data, combining multiple grids, and more. Creating and overlaying 13 types of customizable maps in various coordinate systems, adding scale bars, color scales, graticule lines, profiles, and drawn objects to maps, and calculating volumes, querying attributes, and calculating grid residuals to get even more information from your graphics. To create a basic contour map in SURFER from XYZ data, on the Home tab in the ribbon bar, click the Map Wizard command in the Wizard section. In the Map Wizard Select Your Data dialog, select Browse from the Select File drop-down list. Navigate to your data file and click Open. In the Select Data columns section, verify that X, Y, and Z are set to the proper columns from your data file. Click Next. In the Map Wizard Select Your Map Type dialog, click on the Contour Map Type to check the box, and then click Next. In the Map Wizard Select Gridding Parameters dialog, toggle the Simple Gridding Parameters option. Set the gridding parameters, and click Finish. The contour map is created. Customizing a default map is as easy as clicking on the map layer in the Contents window and changing the properties in the Properties window. The map automatically updates as soon as the properties in the Properties window are changed. All aspects of the map are fully customizable. In no time, you will have the professional quality maps you need to display your data. To see some beautiful and complex maps that SURFER users have created, browse SURFER's online image gallery. This concludes the introductory video for SURFER. If you have any additional questions, please contact Golden Software.
So if you don't have SURFER, you can download a free trial from goldensoftware.com, the /product/SURFER. As you saw in the introduction, SURFER is a wonderful tool for representing your data in two-dimensional and three-dimensional ways. So you click here on free trial and just sign your name, your email address, fill these questions and click send, and you will get a free version that basically has unlimited access to all the features for a couple of weeks. is a good investment, and I strongly recommend that you explore also the other products from Golden Software like Grapher. Strater is for making stratigraphical columns. Voxler, we will have an episode on Voxler because I use it for quick resource estimation. Map Viewer, Digger, all these software are very inexpensive, very useful, and I recommend that you explore them. So let us start by opening SURFER. I am using version 16. When you first open the software, it will allow you to determine a project folder. You set a project folder, you just click here, and I have created my folder right here on the desktop, which I call Golden Droplets 24. So you click select, and now you have all the files there. So let's close. Before opening our first variogram, I want to show you some information. And I wrote once that variograms is a combination of art and science. Here in the next 3 slides, I will show you the most common forms of variograms. So the art here is that you need to figure out which of these forms is the closest one to your variogram. Okay, so let's go back here, and I'm just gonna open a variogram so you will see what I'm talking about. So you click on grids, variograms, new variogram. I have my data here. It's the data of an elevation of a sector in Canada. And that straight line there, that is your variogram. And this is the actual model. So you see, you need to find something that is more or less curved. This straight line will not work well. So coming back here, you will look at this thing and you say, okay, probably this exponential model is the closest one. Okay, but in general, the way you do this, there are 3 basic forms. It's the linear model in case of your data is in a linear, exponential model if it curves in a soft curve, and a spherical model if it's suddenly flat. So definitely our model is the exponential model. So you click inside and you go here to model, and we will start by removing this model, the blue line. Click twice on remover. That's it. And now we will add the exponential one. Okay, and click on auto fit. Click OK, and you get a curve. Of course, this curve is not exactly on top of the real data, so we need to adjust this. There are 2 parameters that you can change. One is the scale, which is represented by y-axis, and what you need to look here is to find at what point the curve starts to flatten. So I will say 19,000 more or less. So I will put here 19,000. The other one, the length, and again you need to find out where the curve starts to flatten. So I will say somewhere around here. So let's say 0.28. So as you see, as soon as I do this change and press enter, the curve adjusts. Now, there is again, this curve starts at 0. We need to add a nugget effect. The nugget effect will displace the beginning of this curve somewhere. We need it somewhere here, let's say around 3,000. So for that, add a nugget effect. Add the nugget effect, click OK, click out of it, click OK, And now the curve is almost where we want it, but we still is to the right of this thing. So let's increase the nugget effect up to 3000 or 2500. Just test like that, enter, and we get a much better curve. Now let's go back to the exponential, and I will change the value of the lag distance until I get the best possible curve. So if I put 0.15, it's too much. If I put 0.2, still is good, but I think 16. So after some testing, we have found a model that follows almost to perfection our original data, and the values were a scale of 16,500 and a length of 0.15. Now, one thing that I usually do is to copy this information into the variogram, because afterwards, when I'm going to export this as an image, all the information gets lost. There is no metadata related. So what I do, I just use the snipping tool that comes with Windows, and select this piece of the data, copy, paste, and then I save the whole file. This way I have the variogram and I also have the components. Okay, and this variogram gave us also an angle of anisotropy of 163.4. Now, to finish with the variogram, we will do a little bit of cleaning. Click on plot, and we will change the name. We'll put proper name, elevation. Okay. Now, down here in variance, click on enable, and this point of intersection between the model and the variance is a very important one. It means that your variogram is good. Sometimes you get variograms where the variance is up here and the variogram is down here. So in those cases, you can use it, but it's not guaranteed that it will give you a much better result. And the last thing, I deselect the subtitle. So this is how I present the variogram. So what is 163.5 means? If you are imagining, a normal scale from 0 on the top, 90, 180, and 270, 165 would be something, let's say, oriented to the southeast. But in SURFER, the 0 degrees is not on the north, it's on the east. It's an east-west is 0, north-south is 180. Okay, so we need to transform these values in order to understand geographically what they mean. I have done this little conversion table for you to convert from SURFER back to the real world data. This file, this PowerPoint presentation, together with all these supporting materials, including two text documents, one on variograms, another one on the support for the video, will be in Mendeley, and I will put a link so you can use this data and read this with more detail. So this is how you transform. In our case, it was 162 something. So it's in the quarter of 90 to 180. So you just add to 160, 180, and you get the 300 something. So in reality, it's going to the northwest. This is very, very, very important. So that is basically variograms. Now, we're going to talk now about gridding. Okay, if we go back to SURFER, we are here at grids. We're going to start gridding our data. So when you click grid data, we open our data. You have here all these ways of doing the, the gridding. You have invert distance, gridding, minimal convert, curvature, modified shepherds, etc. So which one will you use? That depends on many factors. It depends on, first of all, if you are interested in expanding your data beyond the real data. For example, you have data up to here and you want the anomalies to extend up beyond the data. In that case, you will use screen or modify shepherd method. And if you don't want that, then there are other methods. And let me show you just quickly the difference between these things. For example, this is screen and modified shepherd, which extends the anomalies beyond the real data. Okay, there are others like the inverse distance. It also does the same thing. But natural neighbor, you see, it cuts the it doesn't expand beyond the real data. This is very useful. I usually go with extrapolating the data. One of the best that is the minimum curvature, or also the nearest neighbor. Another fact to decide if you which gridding method you're going to be using is the fact how many samples do you have. You have few samples or you have too many samples. And the third factor that you need to figure out is, are you going to use faults or break lines in your data? So I created this flowchart bigger. So you start by asking yourself, you have less than 10 values, 10 samples, then use green or radial basis or polynomial, one of these three. You have less than 120 samples, then again, green and radial basis using the multi-quadratic function. Now, if you have less than 1,000 samples and you don't want to extrapolate and you want to use faults, then you need to use the inverse distance or the nearest neighbor. If you don't want to use fault, then you can use the triangulation with linear interpretation. If you don't want to extrapolate, but you want to add faults, again, creating a radial basis, and if you don't need faults, then natural neighbors. You have more than 10,000 values, and you want to extrapolate, and you want faults, then it's inverse distance or the nearest neighbor. This is perfect for soil sampling data. If there are no faults, then the triangulation or the natural neighbor. If you don't want to extrapolate, but you want to use faults, then it's minimal curvature, kriging, radial basis. If there are no faults, then polynomial. So in our case, we have more than 1,000 samples, and we want uh, to not to extrapolate, and we want to use faults. So one of these will be okay. So let's do it. So let's use screen. You need to have your variogram open. You click advanced option and then you click here get variogram. When you get the variogram, the software will use the anisotropy when estimating the grid. Then you click OK. And then you save your data in your folder. You put, I was using green, so I'm selecting this, save, yes, because I have it open before. And now I click OK. And the grid is created. So if I look in a new page, home, contour, and I will use the elevation grid, you can see here the anisotropy, the orientation of the data, and this is how your data will look like. Now, let's say that you want to have this data with a fault, okay? So how do you create a fault? It's very simple. You select the map, and then in Map Tools, you click on Digitize. And let's say there is a fault. Let's assume there is a fault like this, okay? So you click, let's say, first point, the fault was here, then second point, third point, and 4 points. So we have 4 points. And here are the coordinates of this thing. The only thing that you need to do now is to click at the beginning of one, press enter, so you will have a blank space there, and just put the number 4, the amount of intersections of points that you decide to have. Okay, so we save this, you save as, and it will save as a BLN, as a blank data, and we will call it faults, or fault. Save. So let's repeat the whole gridding process. So grid, go back to the variogram, okay, grid data, open the data, clicking advanced option, get the variogram, but now we're going to add the fault or break lines. And for that, you just need to open this file that we created and say, okay, let's save it again as elevation green, but we will put it elevation green with fault. We click OK. We have the grid. So let's open a new page and compare. I will first open our previous map, the elevation green. This is how it looks like with anisotropy, and remember that we did a fault in this direction. And now I'm gonna create the map for the green with a fault. As you can see, look, compare this bird when the fault passed by. Now there is a fault here. So if you want to see the actual fault, you just go to adding a layer, base, select the fault, and now we have the fault in the map, and you can see how it affects the isolines. So with this, I believe I will stop. I thought I could do the whole SURFER in one episode, but it will be too long. I think that it was great that we could cover the variograms and the gridding. And on Golden episode number 25, I will be talking about mapping and all the tricks of the trade and how do I customize my maps. So with that, I thank you all for your attention. I wish you all health, both physically and psychologically. And see you next week on Golden Droplets, episode number 25. Bye.